Okay, good morning.
Morning.
So we're starting our, whoops. There we go. Starting our second module this week on finite state machines. We'll have 3 weeks on models of computation. Finite state machines this week, stack machines next week, Turing machines the following week. And there's 2 assignments that will be due for the finite state machines. The first one due this Friday and the next on Monday, the 14th. I haven't posted those yet, but they'll be posted by tomorrow. The notes are online. And for some of you, the finite state machine portion of this will be review, which is fine. Most topics gain value by being shown to you twice as you go through your academic progressions. And then what we'll do is build on this and go from finite state machines to stack machines, which is a pretty simple transition, and then from there to Turing machines. And what we're doing is we're climbing up the Chomsky hierarchy in terms of computational power as we go through these. Okay, the outcomes, again, at the end of the week, convince yourself you know this stuff. All right, why do we study these things? This class, depending on what university you're in, can be highly theoretical or highly practical. And the practical form follows along the lines of, how do you do an if statement in Ruby? How do you do an if statement in Perl? How do you do an if statement in JavaScript? I don't find that much value in that because you can find all the language syntax just by reading the documents for those specific languages. The highly theoretical version focuses entirely on these theoretical aspects and models of computation. So we do a little bit of both. We do these theoretical aspects, but we also do some practical aspects, particularly introducing the functional paradigm later in the semester. So the value of finite state machines have both theoretical and practical value. The theoretical value is this, the core question in computer science, the single most important question is, what can a computer compute? Everything is boiled down to that. Computer science is broken up into different large categories, one of which being formal languages, computation theory, one of which being architecture and machinery. They're all still trying to answer that core question. What is it that a computer can do? And in order to answer that question in a formal way, we need a formal model. Well, what's a formal model? A formal model is a non-ambiguous system devised by humans. And we tend to think of mathematics. Mathematics is a formal system. Programming is a formal system. And so we need a model, a math model of what computation is. And I posted a question on the discussion board. What is computation? Most of us, when I ask that question, what is computation? Most people say, oh, it's about calculating a number or calculating some property of a system. And again, just like we learned with languages, that's an application. That's a usage of computation. Actual computation, what it is, not what it's used for. What it is mindless rewriting of symbols. So I have a symbol. I have an operation that I can perform on that symbol, and if I perform that operation, I get a new symbol. There's no meaning there. When we apply that to things, that's when we start to inject meaning into the system. So by formal and by computation, let's go backwards. Formal systems. All formal systems have the following properties. They have a small number of things and a small number of operators that operate or modify or rewrite those things. And then they gain complexity through iteration. And you can think of Boolean logic. It has a small number of things. It only has true and false are the things. Those are the only values that are allowed. And it has a small number of operators. The and operator, the or operator, and the not operator. And from those 2 things and 3 operators, you get all the complexity that Boolean logic allows. Which means, those of you that took the digital circuits class, all the digital circuits you ever created are created from those things. Some people say there's even fewer things. Some people say there's only one value, true. And the false value is actually the not operator applied to true. And some people say that there are only 2 operators, the and the not. And again, those of you that took digital circuits know that you can create any circuit from NAND gates, right? Not AND gates. So the and the not operators are sufficient to create the or operator, which means really, if you really want to pare that system down to bare bones, it's only got one value, true, and it's only got 2 operators, and not. And from there, you can create false, it's not true, and you can create or because it's a combination of the ands and nots. So computation is the same. It's a small number of things and manipulations. Now we can create any kind of manipulation we want. You can create your own formal system. You can create your own absolutely do nothing, means nothing formal system. Pretty trivially. The formal systems, the computational systems that survive end up being useful towards some application. You know, you can apply them. So we have mathematics. Why? Well, gosh, that's awfully useful. You know, it used to be useful to count how many sheep and goats you had, and now it's useful to keep track of how many of any things you have, in addition to modeling dynamics and modeling statistics and things like that. So the whole idea here is, remember that computation is mindless manipulation. And the finite state machines then fall into that category. They are mindless entities that can be performed by an automatic device. And it models some form of computation. Now, if you look in the Chomsky hierarchy, you know, we'll do this towards the end of the lecture. If you look in the Chomsky hierarchy, the model of computation that we're dealing with finite state machines are relatively weak. If we think about all computation that a computer can do, all computations that can be performed, and people have studied that, then you come up with a set of problems that can be computed and a set of problems that cannot be computed. And it turns out, you know, Alan Turing used the Turing machine for that. Alonzo Church used the lambda calculus for that. They both came to the same conclusions. The Turing machine can represent all possible computable problems. The finite state machines cannot. So they are weaker in terms of computational power than the Turing machine. Oh, by the way, when you see a computer being advertised on TV, they love to talk about the power it has. This computer has more power. No, it doesn't. All computers have the same amount of power in terms of Turing machine computability. They can all do the same stuff. Some of them take longer. That's the only difference. So when they say more power, what they really mean is we have a faster chip, we have more memory. But in terms of power, when you think of it in the computer science sense, they are all equivalent. Okay, they also have practical value. Finite state machines are used a lot. When you want to model a system, what do you tend to think about? You tend to think about, well, the system has state. This is the whole idea behind the object-oriented paradigm, right? That things have state. And when I do something to the system, I change its state. We can call that a transition. We transition from state to state. And you know, the classic finite state machine that we've all used is a soda machine. It has a state And the state, when you first walk up to it, it has some number of soda cans in it. And you have put $0 in, and then you put in a quarter and it changed its state to now, oh, okay, now you've put in a quarter. And you put in another quarter and it changed its state again. Now you've put in 50 cents. And you can keep changing the state all the way up until you put enough money where you can buy a soda, and then you press the purchase button and it will dispense a soda and it will change its state again. It will reduce the number of sodas that it has by 1, and it will go back to you have put no money in. So these are all state transitions, and they're very discrete and clear in a soda machine. Not all state transitions are so clear. A car has some really clear state transitions. On and off, right? You can turn it on and you've gone from the off state to the on state. Occupied and unoccupied. Doors open, doors closed. Doors locked, doors unlocked. All of these are very clear states. What about when you go from 20 to 25 miles an hour though? There's some weird state transitions there because the change from 20 to 25 miles an hour was continuous. But that's okay. You can model it as if you went from 20 directly to 21, directly to 22, directly to 23, 24, 25, as if you skipped all the intermediary values. You can model it that way. And quite frankly, if you have a digital speedometer, that's exactly what it does, right? It doesn't give you your speed to the 30th decimal place. It gives you your speed in whole integer value miles per hour. So it's modeling that state. If your car tells you the temperature outside, it probably also models that state, those states as discrete. It's either 76 degrees outside or 77, but rarely do we see 76.2498434, on and on and on. So in the real world, you can model things as state, and it's really done. This is actually done. There's a whole system of testing software, testing systems, the verification and validation of systems where they model the system as states. Some states are considered bad states, and then they play with the system and see if they can ever get it to transition to a bad state. If they can, there's a design flaw. Take a traffic light, north-south and east-west. If north-south is green, east-west should be red. That's a state. And then the traffic light can transition to where north-south is red and east-west is green. That would be a state transition. I'm skipping yellow, but that would be a state transition. If we ever went to the state where everybody has the green light, that's a bad state. So you can model systems and then start to inject signals into those systems or inject actions onto those systems and see if you can get it to go to a bad state. That's a legitimate thing that people do to try to determine if they have a good design or not. And those of you that take SC 410 will explore that topic at length. What we're going to consider finite state machines in the context of languages, and we're discussing languages and grammars and models of computation, they all kind of roll up into one topic at this point. What we're going to treat finite state machines as are language recognizers. So we already have the idea of a language, right? It's a set of strings. And we already have the idea of a grammar. A grammar can produce the set of strings. Now let's add to that a recognizer. If I have a machine that is designed to represent a specific language, and I feed it a string that is in the language, that machine, if it's a language recognizer, will tell me if that string is in the language. And if I feed it a string that is not in the language, that machine will tell me this string is not in the language. The typical terminology that we use is called accepting and rejecting. So if I have a language and I take a string that I know is in the language and I feed it into that machine will accept that string. If I take a string that I know is not in the language, the machine will reject that string. So now we have language recognizers, at least the idea of it. So what we can do, if we don't know if a string is in the language or not, we feed it into the finite state machine, and if it accepts it, then we know that string was in the language, and if it rejects it, we know that string was not in the language. This happens all the time in the real world. We're doing it now. All of the data that is being sent to you via the internet is happening using specific formats, internet protocol formats. And those internet protocol formats, which I don't know, are probably 1024 bits long, and the first, n bits are going to be maybe a timestamp, and the next n bits are going to be sending IP address, and the next I bits are receiving IP address, and then there's going to be content. But basically, in order for something to be, say, a valid IP address, it has to be a specific sequence of ones and zeros that's in the language of IP addresses. And as long as your machine keeps parsing those and recognizing that those are valid IP addresses, everything's fine. If not, then that string will be rejected. The data will be rejected. So this happens all the time. There's also things like, when you send a message, maybe it has to begin with 8 zeros and it has to end with 8 zeros. There's things like that that people will develop just to identify what is a valid and an invalid message. What do they mean by a valid and invalid message? It's either in the language or it's not. The language of messages. I'm pausing here for questions. Okay. And again, if you have questions, just unmute yourself and speak up, and that'll work out just fine. If you're more comfortable in chat, that's fine also.
Hey, I have a quick question.
Very good.
It's not about this, it's just a general question I meant to ask earlier. So just to verify, the assignment is due tonight, even though we only had 24 hours?
That is correct.
Okay. There is no possible way we can get an extra day.
That is correct.
Okay, no problem. Thank you.
All right, so let's review. Language. A symbol is a distinct mark, an alphabet is a set of symbols, a string is a sequence of symbols, and a language is a set of strings. And a grammar, at least in the Backus-Naur form, is a set of production rules by which you can create the strings that are in the language that the grammar represents. And the grammar has to be able to create all of those strings, and it has to be able to create only those strings. In other words, strings that are not in the language cannot be produced by the grammar. And we've talked about the Chomsky hierarchy. We've talked about it in the context of the grammars, right? The characteristics that the grammars take on. Now let's go and review the Chomsky hierarchy in the context of models of computation. So the regular languages match to finite state machines. Finite state machines are also known as discrete finite automata. So when you do Googling, or if you're watching other people on YouTube for this information, you may hear them using that language. Finite state machine means you have a number of states, but they're finite. Discrete finite automata. Discrete means that the transitions are discrete, meaning you can't transition halfway, right? So in the context of our car, you went from 20 miles an hour to 21 miles an hour. You didn't visit any of the miles and hours in between. And finite means that there are a finite number of states and transitions. And automata means that it can perform its operation without human involvement. It's automatic. The biggest weakness of finite state machines is they don't have memory. So remember the rule with the regular languages? One of the rules with the regular languages is you had to be able to produce the string from left to right or from right to left. And if you have to produce the string from left to right, let's say, then you don't have to remember what you did in the past. You just keep merrily going on with your string. But the context-free languages, if you can create things in the middle, then you have to remember, oh, wait a minute, there was something that I left unfinished previously in the string, and I have to go back and finish that. you have to remember things. So the biggest difference between the finite state machine and the stack machine is the introduction of memory. And the memory that we introduce is very simple. It's a stack with all that that implies. Remember, a stack, you can only access the top element of the stack. Sometimes they're called push-down automata because push-down, you're pushing things down into the stack. The next level up is the Turing machine, and the big difference between the Turing machine and the stack machine is that now the Turing machine effectively has random access memory. It's always framed in the context of a tape, but now you have access to any of the data elements that you want. So if you look at how this progression goes, we start out with finite state machines with no memory. Then we go to stack machines that have stack memory. And people get really exotic with that, with multi-stack machines and things like that. And then we go to Turing machines, which have effectively random access memory. So it should be a relatively seamless transition as we go from one to the next to the next. The finite state machines to stack machines is a pretty nice, simple transition. Once we go to Turing machines, there's a bit more notational changes. So it might take a little bit longer for you to feel comfortable with that. I'm not spending much time on Turing machines. We're going to do that for a week. And the assignments, you only have one assignment there, and it won't be that detailed. But be aware, there are entire courses, and I've taken them, where all you talk about are Turing machines. So there's a lot there, right? We're just skimming the surface. All right, I think this is a review slide. So we say that the finite state machine will accept all the strings in the language that it is designed for, and it rejects all strings not in the language. So one-to-one correspondence, that's not true. There's a correspondence between finite state machines and languages. By the way, for a given language, how many grammars could we create again?
A potentially infinite amount.
An infinite amount, that's right. Most of which are bloated and useless. And the same thing's going to happen here. So for a single language, there are an infinite number of finite state machines which are correct. Most of them are useless. Trivial point, all finite languages are regular. Well, let's see, why am I saying that? Because there's a correspondence between finite state machines and regular languages. So what we did previously, I said, okay, here's a language, make a grammar, and now give me a justification as to why this language is regular. And you said, well, it's regular because the grammar has on the left-hand side only one non-terminal, and on the right-hand side, the terminals never decrease, and we're creating the string from left to right. In other words, you could say, based on the characteristics of the grammar, that this was by definition, a regular language. We're going to do the same thing with finite state machines. If you can create a finite state machine for a language, that language is regular by definition, because there's a correspondence between the regular languages and finite state machines. Now, you can create an infinite number of finite state machines, most of which are bloated. Now, I went off on that tangent on a tangent. So the only way I would say that you could have a number of finite state machines that were not infinite for a language is if the language itself is finite. But it does turn out that all finite languages are regular. Why are all finite languages regular? Because you can brute force a finite state machine to accept every string that's in the language. If there's 1,000 strings in the language, that's finite. You can create a finite state machine that probably has a couple thousand nodes of states in it. But it brute forces its way to accept every possible string in the language. The fact that you can do that, the fact that you can create a finite state machine is proof that that language is regular. You could also brute force a grammar. It probably has a few thousand rules in it. By the way, did anybody look up the grammars for Java, for C? There's only I don't know, Java has maybe 150 rules or something like that. Okay. Formal definition for a finite state machine. Once we start doing this, people start to freak out sometimes. It's all set theory. Notice everything comes from set theory here. Strings are, languages are a set of strings. And finite state machines are going to be defined in terms of sets of things also with a transition function. So we always say that the finite state machine, and I'll use M for machine, G for grammar, L for language. The finite state machine M is, now when you see these curly brackets and then you see Q sigma, Q naught, F delta, I'm going to start using the word tuple a lot more in the course. A tuple is simply a sequence of symbols or a sequence of things. So this is a 5 tuple. You're used to a 2 tuple because you all took algebra and you're used to the XY coordinate system. And when you did points, they were always expressed in terms of X and Y. That's a 2 tuple. And when you went to 3 dimensions, you did X, Y, and Z. That's a 3 tuple. Well, finite state machines are a 5 tuple. And the 5 tuple is capital Q, a finite set of states. That's why it's a finite state machine. Sigma, which we're already familiar with, that's the alphabet. Q naught is the designation for the state that you start in. F, capital F, that's the set of final or accepting states. And then delta is the transition function. So, capital Q, again, when you go online and look for other information about these things, sometimes you'll find authors use capital S instead of capital Q. That is a style choice. I'm going to use capital Q, and I'll almost certainly use lowercase q for an individual state and capital Q for the set of all possible states. And other authors will use capital S and lowercase s. No difference. Other than that, I think people tend to keep things the same. Notice, by the way, if we say that Q is the set of states that the machine is composed of and sigma is the set of finite symbols, then this has to be true, right? The start state has to be an element of the set of states in the machine. Why would you start outside of the machine? That has to be true. And also, the set of final states has to be a subset of Q. And delta is a transition function that we have not yet defined or described, but it will specify how to transition from state to state. Okay, I put these things out here almost as afterthoughts, but in a formal system, these are actually critical to keep these things here. Again, in a formal system, everything is fully defined. And as you start to move into more complex things, those things start to matter more. All right, what is the operation? How do you use these things? Well, we start in the start state. What a surprise. So if you're going to process some string, you start in the start state. You haven't done anything yet. You haven't processed anything yet. Then you process the string U one symbol at a time from left to right. So you take the first symbol in U and you process it. And the way you process it is you say, okay, I'm in Q0 and I just saw A. What does the transition function tell me to do? And it's going to tell you to go to a new state. So you're transitioning to a new state. And you keep doing that until you run out of symbols in U. So you keep processing U from left to right, keep doing it till you run out of symbols, and then look where you are. What state are you in? If you are in one of the final states, you accept the string. And if you are not, then you reject the string. So if the machine was built correctly, every string that is in the language, when you process it, you start at Q0 and you'll end up in one of the final states. And if the machine was built correctly and you feed it a string not in the language, you start at Q0 and you end up in some state that is not a final state. So again, some people will call the final states accepting states. How is this done? What does this look like? Well, once we move to the graphics portion, life gets better because we are, as humans, we love graphical stuff, right? Picture is worth 1,000 words. That's how we take in information. So how do we draw these things? This is universal. A single state is simply a circle, and you put the name of the state inside of it. And I'm going to use Q sub I and Q sub J for generic state.
Professor?
Yep.
Is this PowerPoint on Canvas?
Yep.
Okay, I'm sorry. I have a senior design meeting that just got pushed to now, so I have to go attend that.
Enjoy. I also have the recorded lectures up.
Oh, okay, perfect.
Okay, and this should be up by tonight.
Okay, thank you.
All right, have a good meeting.
Thank you, I will.
All right, so we're drawing these with circles and arrows. So your generic state, non-accepting state is just a circle with the name of the state inside of it. The start state is a circle with a little duck beak drawn on it. Some people use an arrow. I use the duck beak. And then the final state is a double circle. Transitions are shown using arrows, and the arrow is labeled with the symbol that caused the transition. So in the bottom there, if I'm in state QA and I'm processing in, I'm sorry, if I'm in Q sub I, and the next symbol I'm supposed to process is an A, then it will take me to Q sub J. So the graphical form of the machine is telling me that I'm supposed to go from QI to QJ if I'm processing an A. And again, those of you that took CS222 and some of you saw this in CEC220, you saw some version of this in CEC220. The formatting may be a little bit different. The CS222, this would be consistent. Not every semester of CS222 over the last few years covered this, I believe. Okay, so what does this look like? Here's an example. All strings having one or more A. Now, how do you create these things? Just like you did with grammars, start thinking about what is the smallest string? Then what's the next smallest string? What's the next smallest string? And then you keep creating them, and you keep building up your machine until you've created those strings. Once you convince yourself that you've covered all the strings that's in the language, then you can think about, okay, now what about the strings that are not in the language? So that's how I tend to build these things. I tend to build them up. What's the smallest string? What's the next smallest string? What's, what? Sometimes you have different forms of strings. What's the first form of the string? What's the second form of the string? And I build the machine up to have all of the strings that are in the language represented. And then I say, okay, what about strings not in the language? What am I going to do with them? So the way this works, all strings having one or more A. We're cruising along, B, 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 okay, not in the language, not in the language, not in the language. I get that first A, B, 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 A. Boom, I'm in the language. Once I'm in the language, right, once that string is determined to be in the language, in this case, it can never leave again. So what I'm going to do is immediately transition to a final state, and then I'll make sure I stay there. So this machine looks like this. Now we can create an infinite number of these just by adding more final states. I'm in Q naught and I see B, 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 B. Oh, okay, so let's build it the way I said. All strings having one or more A. What's the shortest string? A. Okay, so I'm in Q naught, and the string A takes me immediately to a final state. So you'll see I drew that arrow to Q1, which is a final state. Once I'm in there, I will always accept that string. So I make that curved arrow that goes from Q1 back to Q1, and I label it A comma B, meaning, look, you can get an A or you can get a B. Either way, you're staying in Q1. And then I start thinking about longer strings. Wait, what about strings that begin with a B? B, 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 B. Oh, okay, I can just kind of loiter there in Q0. I can hang out in Q0 while I'm processing these Bs. And then as soon as I get that one A, I go back to Q1. So I make that circle for the transition for B. That curved arrow means that if I'm in Q0 and I get a B, I just stay in Q0. Now, what are the only strings that will not be accepted here. The strings that will not be accepted are the strings that are composed only of B's. And if you look at the picture, the strings that are composed only of B's always stay in Q1. So when I run out of string, always in Q0. So when I run out of strings, I'm in Q0 and I reject. But if I get a single A, I go to Q1, and no matter what happens after that, when I run out of strings, I'm going to end up in Q1 and I accept. Now all that stuff on the right, the picture on the left is the graphical form, and on the right, it's the set notational form. So now what I do is I take my picture, I take the graphical form, and I just translate it. Okay, capital Q, that's the set of all possible states. Now I can specify what that is just by looking at the states that I have in the graph. Oh, I have Q0 and Q1. Sigma is A and B, we said that ahead of time. Q naught is the single start state, and it happens to have the same name, Q naught. That's pretty much always going to be true. Not a rule, right? But that's how we build these things. There's only one final state, which is Q1. And notice, pay particular attention here, I put that in curly brackets. Why did I put Q1 in curly brackets there? So I say F is equal to Q1, but Q1 is in curly brackets. Because remember, F is a set of final states, so I have to use set notation. Sets are enclosed with curly brackets. And then the delta function is basically, it's a lookup table. So if you look, it says, okay, Q0, if I get an A, right, it's just cross matrix. Q0, I get an A, I go to Q1. Q0, I get a B, I stay in Q0. Q1, I get an A, I go to Q1. Q1, I get a B, I stay in Q1. So that delta is tabular form. Now, the version on the left, the graphical form, we as humans love that because we're very good at processing visual information. You cannot program a computer though to do this. But look at on the right with the lookup table. Computers love lookup tables, right? So if you ever need to program a finite state machine, then you would want to use the lookup table form. But if you ever want to show a finite state machine to a human, you would use the graphical form. Questions? Okay. All strings that start with two A's. Now they have to start with two A's. So let's start thinking through this. What's the shortest string?
AA.
A, yeah, AA. So I'm going to start in Q0. My first A will take me to Q1. My second A will take me to Q2, and that's going to be my accepting state. Now, how can the string get longer? It has to start with two A's, and then do I care what comes after that?
No.
I don't, right. So, okay, so once we start with two A's, we're going to be in that accepting state. I'll make that trick where I just loop the arrow back and say AB, because no matter what happens, I stay in the accepting state. And then I just have to worry about strings that don't start with two A's. If it starts with a B, what do I do? If it has one A followed by a B, what do I do? Well, I need to go to a state where I know I can never, ever, ever accept that string. So that machine looks like this. I start in Q0, the first A takes me to Q1, and the second A takes me to Q2. But if I start with a B, I go to Q3, and notice what happens. Once I'm in Q3, I can never get out. So no matter what happens to the rest of that string, I will never accept that string. I will always reject that string. I call that a garbage state or a trash state. Basically, I threw the string in the trash. So if you construct your machine starting with, okay, the smallest string that works, and then start building on that, thinking in terms of what works, what should go to a final state. And then once you're done with that, then you say, oh, okay, now what about strings that are not in the language? Do I need to throw them in the trash? And it's pretty common to have a trash state. Notice, by the way, Oh, discrete, it's deterministic. DFA, I said it was discrete, it's deterministic. Deterministic finite automata. Deterministic meaning you always know where you're supposed to go. Finite state machines, at least in the way we're talking about them, are deterministic. And by deterministic, I mean this. You always know what you have to do in every situation. And because it's a formal system, you don't get a choice. In a formal system like this, you have exactly one choice or one option for every possible situation. Now, what are the situations composed of? You're in a state and you're processing a symbol. So for every state, you have to tell in your picture there, in your graph, for every state that you draw there, you have to have exactly one transition for every symbol in the alphabet. This is another reason to keep the alphabet small, by the way. So if you notice Q0, the alphabet's A, B, right? The only thing we're going to get is either an A or a B. So if you notice in Q0, I tell you what to do on A and I tell you what to do on B. And for Q1, I tell you what to do on A, I tell you what to do on B. And so on and so on. So when you're building these things, first, I'm giving you process here. Start with the smallest strings. Make that smallest string go to a final state. Then start thinking about how the strings can get longer and what do you need to do to modify the finite state machine to accommodate those. Then think about strings that aren't in the language. Do you need to build a trash state for them? And lastly, just do a quick visual check. For every single state you have, do you have something to do for every element in the alphabet? Now our alphabet is A, B, so we only need an A and a B, but we need exactly one A and a B for every state. So how do I see students forget this? They'll leave off. So I might be in Q2 and you told me what to do on A, but not what to do on B. Or they'll do it twice. So in Q1, I'll have an A, you might see a transition from A to Q2, and then another arrow going from Q1 to Q3 on an A. Well, that's no good because you told me to do two different things if I got an A. It's exactly one. So do that quick check. This, the set notation form on the right, once you draw the picture, that is a trivial translation. So Q, the set of states, it's Q0, 1, 2, 3. And sigma is AB. We said that before. Q naught is Q naught. The set of final states is the set that contains Q2. And then there's the transition function in a tabular form. And because I'm lazy and because I'm not wanting to be mean to you, I think we should all do this, where we just put down the 0, 1, 2, 3 instead of Q0, Q1, Q2, Q3, right? Why would I have to write Q 12 times? And better yet, why would I make you write Q 12 times? Just put the subscripts there. So that is telling us, doesn't match. Okay, if I'm in Q0 and I get an A, I go to Q1. That matches the picture. If I'm in Q0 and I get a B, I go to Q3. Yeah, that matches the picture. Now, when I'm grading these, if your machine is incorrect, but this tabular form that you present matches the machine, you get full credit for that tabular form. I'll knock off some points for the machine, but I'm not going to knock off the points twice, because if your tables match the machine, you did exactly what you were supposed to do. Okay, I've got some more examples.
Professor, I have a quick question.
Sure.
So I don't know if I'm missing something here, but it looks like both Q0 and Q1 are going to Q3, but then I don't see an arrow from Q3 to anywhere. So how do I get to the final state from there?
Oh, you mean from Q3, how do you get to the final state?
Yeah, because I don't see an arrow like going back to Q0 or Q1. So how do I get all the way over to Q2?
Okay, so from Q0, if you get one A, you go to Q1, and if you get another A, you go to Q2. And that's the only way to get to Q2.
Oh, okay.
If you're in Q3, there's no way to get to Q2, and that's how it should be, because what that means is if the string starts, let's talk in terms of the language. The language is all the strings that start with two A's. If the string starts with a B, is it in the language?
No.
No. So since it's not in the language, we should never, ever, ever accept it. So
Okay.
right off the bat, if I'm in Q0 and the first thing I see is a B, I'll go to Q3, and then I can never get to the accepting state, the final state. Remember, Q2 doesn't mean that's where you end up when the string is completed. It means that's where you end up when the string is completed only if the string is in the language, because you're going to accept it. But other strings, for example, consider the string that is only composed of A, the letter A. That goes from Q0 to Q1, and then it stops. So that string would be rejected because it's not in a final state. Now, should it be? Is it in the language? Is the string that is only composed of the letter A in the language?
Oh, because it has to start with two.
Right. So that's what's going to happen. The strings that aren't in the language, they're going to end up in some state in your machine. They never leave the machine, but they're going to end up in some state in your machine that is not a final state, not an accepting state.
Okay, thank you.
Okay. Now, what we'll do on Wednesday, I've got more examples here, and I've also got the same languages that we used for the grammars. I reposted those as practice problems for you, and I think I added a couple more. And I'll draw up the finite state machines for those too, but it would be really helpful if you drew these on your own, because as you know, watching me draw a finite state machine and you actually drawing your own are two completely different activities, and you get far more benefit from the second than the first. So please try some of these on your own. Convince yourself you can draw these machines. And in that language thread, I put up a language discussion a while ago where you guys can post challenges to each other. By all means, put up a language and see if people can create finite state machines for them. Okay, I will see you on Wednesday. If you have other questions, obviously get in touch with me via Canvas. Thanks for being here, guys. Happy Labor Day.
Thank you, Professor.
All right, bye.
Thank you.
See ya.
Thank you.